Okay, good morning, students. Welcome back. We're continuing with the basics, chapter 1 of the Freilich book, Electrotechnology II. Yesterday, where we left off was we were discussing a technique called VDR, voltage divider rule, or voltage division. And it's basically a new technique where you're able to quickly find a voltage within a CD circuit. Voltage division only works for CD circuits. Just a quick recap again. For instance, if you have a source voltage there, and then of course that is supplying a current through those resistors. And if you quickly want to find the voltage in whichever individual resistor, you have to take the source times by the resistor that you want, and then divide that by the total amount of resistors. So that's just voltage division. We will be doing current division after this, and then and you basically see. So what I like us to do is this example, right? This is in your textbook. I think it's example number 1. Could be a test level like question. So over here, we are required to use voltage division to find that current. So let me prepare my blackboard. I hope we'll do this example together. So to ensure that you get the idea of what's happening here. I want to see, and it clearly states that we're supposed to use voltage division. So that's what's going to be expected of you. Let's open that. So we're doing a few circuits today to get you back in the game. And the circuits are going to get a bit advanced. You might have around 3-4 branches. So 1 branch, 2, 3, 4. And then I'll validate my results with LT-Spice, which I showed you guys yesterday. And I'll post a link to that at the end of this lecture. So I'm just going to prepare my blackboard quickly. So I can get you guys in. So I'd like you guys to, I want us to do this together, obviously. So let me just quickly share. I've got 12 students, that's good. A whiteboard. Fantastic. Okay. Sure you guys can see it now. Great. Okay, so what is required for us is to find the current going through the 4 ohm resistance, or IL. Right, so how are we going to do this? Who can tell me? What's the first step in solving this?
Actually, this circuit, yeah, for voltage divider just work on series circuit, so we need to put it in series.
You mean parallel series?
Yes, 6 ohm and 4 ohm are in parallel, so we can put it in series, sir.
Oh yes, that's correct. Yeah. So what we have to do now is take that 2 guys and put it in. What is this? Oh, sorry. Put it in parallel, right? So I'm going to go with the long way here. So we say odd 4 parallel to 6, or 1 over, equals 1 over 6 plus 1 over 4, right? Of course, you can just get this in a calculator. Let me get mine. I'll show you a quicker way to do that, by the way, but we'll get to that soon. I'm just going along with it deliberately. There's a question over here. Is it a question? 2.4. Oh, okay, let's just see about that. And if you do that, you'll get a value of 2.4. I hope everyone can do that. Because the guys, remember, this is still child's play. Pen is the thick. I like this thickness. Yeah. Fantastic, right? So with this, we have a new circuit now. And I want to just show you also, while I'm at the mark allocation of how I normally mark. So while I'm here, I might give a mark here and a mark here. But if you don't have a unit here, I'll mark this wrong. I hope that's clear to everyone. So that's just an idea of how marks is being allocated. So if you have no unit, no mark. We engineers, everything is physical quantities, everything has a real life significance or practical significance, so we expect units attached, right? So if I could just re-sketch the circuit for you, just wanted to re-sketch it, but the idea is that this guy falls away, it falls away, and this new value here becomes, just erase that, 2.4 ohms. So we've got a circuit like that now. So we don't actually have the circuit over here. So the whole point of this is to actually kind of reduce the circuit so that it can be convenient for you to analyze, right? And again, okay, I'm not going to redraw that. So we're all happy now that we have a series circuit, right? It's 3 volt, it's a 3 ohm, 2.4 ohm, and a 9 ohm. We're all on the same page there. We all agree with that. We have a series circuit. The 3. Thank you, CISO. And then what we can do now is find. Yes, Mr. Neto. Oh,
No,
okay.
I agree with this series circuit, yes, sir.
Okay, great. So now what we can do now is apply our voltage division. And the reason why we're doing that, so okay, for the first question is where do we apply the voltage division and why? Does anyone have an idea? Can you raise your hand on the chat, or you raise your hand on Blackboard? Your hand should be there somewhere. So where are we going to apply the voltage division and why? This is what I want to know. Anyone? Okay, don't like anyone's. So where we're going to apply the voltage division is across the 2.4 ohm by this branch, and the reason why is because this guy and that guy and the 4 ohm is in parallel, and if they're in parallel, they have the same voltage. From that same voltage, then after that we can actually divide out by. Then we can divide the voltage by the resistance, and you'll get current. So I think I should actually sketch this, especially starting up here. I don't want to. Okay, so that's a 3 ohm, and now it looks like this. So we have a simple CD circuit. So like I said, so as a 75 volts, we've got 3, 2.4, and 9. So now we're going to find the voltage across here. So how does voltage division work? We want it across 2.4. So we take our source voltage, we times by the one we want, and then we have to tally up the resistance. So that'll be 3 plus 2.4 plus 9, and you should get a voltage. So we're going to find the voltage at this particular point. Right? I hope everyone agrees with me, and you should get a value of, what is my value? 12.5 volts. Right? Makes sense. One thing you should always check with this is, got Mr. Siyama here. Welcome. One thing you should always check is that, remember, I mentioned to you that you can never have a voltage higher than your source, right? Remember, this is supplying energy to the circuit. This energy is being distributed amongst here. So there's 12.5, therefore that means there is a 62.5 will be distributed between the 9 and 3. Obviously, the one with the higher ohm value or the higher resistance will have a higher voltage. So always think about it. If you need an answer of 80 here, you know something is not right. You should look how the voltage is distributed. Nevertheless, what I'm going to do now, I'm going to expand this branch over here, right? So we're going to have a branch like this, and I'm just putting this in parallel. I'm just going to go to the next. So my approach is normally I draw a circuit and I solve my simplified circuit and I solve. Oh man, to get it nice and straight. Could have actually just done this actual resistor symbol. It's like a coil, but anyway. So we know across the two resistance we have a voltage of, potential difference of 12.5 volts. And of course here this was now I'm basically reverting this back into its two branches, and that was a 6 and a 4, right? So if I want the current going through the 4 ohm, I'm going to have to say I 4 ohm will be equal to the voltage. The reason why the voltage is the same, so V6 equals V4 in this case, because it's a parallel arrangement. If you agree with me, it's 12.5 divided by 4, and that's going to give us a value. So divided by 4. The answer should be 3,125 ohms. Amps. Is everyone happy with this? So you apply voltage division to that particular. Okay, so that's great. I hope everyone got pulling. Are you fine, Michaela? Hope you get that. Simple enough. Okay, that's just small practice with. So Pauline, what don't you understand? Let's just try to help Pauline here before we move on. Oh, so what I did now, right, is that we found the voltage across 2.4. So, okay, first thing, we first found equivalent resistance from the 4 and 6. That's in parallel. We get that part. Then we take the two. Then we find the voltage across the 2.4. And the reason why we find it across them is you know the voltage is the same. Let me just erase this. Remember, this is parallel over here. So the voltage here is exactly the same as the voltage over here. That's the reason why. It's basically over here at this place here. And then once you find the voltage, I am just basically arranging it in a way that it looks like it's parallel, because they are essentially parallel. I mean, and now we know, and because they're parallel, we know that the voltages are the same, and you know, current split. Then we can find the current going through the 4 ohm resistor. If, for instance, to make sure that we're correct, another thing we can do also, we can also find the current in the 6 ohm resistor, and that's going to give us 12.5 divided by 6. So this is the answer I wanted. I'm just doing this. So the 12.5 divided by 6, yes, that's correct. We'll give it 2,0833 amps. That's another, just, and of course the total current coming in here. So what I mean, the total current coming over here in, going here, we can just call it IT, I total, will be I4 plus I6 will be IT, and then this will be plus 3.215. I think it's 5,2083 amps. So pulling, I mean, of course, I just kind of went extra up with extra here. This is what you just need, but that's the idea. I hope you got that. Okay. So I digressed a bit over here, and so to agree with me, the current going through the 2.4 ohm resistor, which is basically coming in here, is 5.2083. You guys agree with me? So to confirm that, I'm just gonna check for the total current. Basically going back over here using the circuit over here, the circuit over here. So I'm just doing a quick check. So to find the current here, of course, it's going to be simple. It's the voltage divided by 2.49. 3 plus 2.4 plus 9. And of course, I'm expecting a current of 5.2083. I'm just showing you different ways of looking at this. I know I'm supposed to be what voltage division, but I want to just show you how you can view it to make sure that everything makes sense. You guys see that? So that's a total current. Two different ways. So everyone on the same page. I know I'm talking about voltage division, but I wanted to just have a holistic perspective on how to solve these circuits. Okay, thank you. So now I'm going to go back to my slides and I'll do some practice. Some practice, and then I'll go back to explaining, and then we can solve more circuits. All right, we're back, and let's move on. Now, of course, you guys are aware of parallel circuits. They're defined as two elements, branches, or networks are in parallel if they have two common points. Right? Obviously, we know this. We know that they're showing different ways of how parallel looks. So, like if you look at the figure A at the bottom, can you see it's like basically what we had? Another way of looking at it is also figure B. That's how I sketched it. Or it looks like where the current or whatever the conductor is, it's like vertical, and this one's more horizontal. And then we've got a very funny configuration over here, but essentially means that the voltage across A and B is, it's the same. It's the same voltage. So that's just different ways of how it looks. Again, this is the norm of what looks here, of how parallel circuit looks. That we know the I, which is the total current, is the sum of the individual currents. Obviously, our students, if you want to understand electricity flow in particular, always think of it just as a pipe. Think of water in a pipe. So if you had water flowing, so think of this as a voltage as a pressure source. Let's say it was a water tank, and you discharge the water tank. So you open the valve, flows through this pipe, and then it will split. Some water will go into this part, some water will go straight, some water will go to that part, some water will go into the I1, I2. So it's exactly the same as fluid flow. Yeah, fluid flow in a liquid state or in a gas state. Okay, just a recap on parallel circuits. Now, same thing, just basically putting all the symbols over here. How we can find the individual currents. Obviously, we all know this, and that's the total currents. But what I want to introduce to you is a new thing, as the product sum rule. So if you have two resistors, for instance, and this is for two resistors, a special case for two resistors. Mathematically, you can quickly just find the equivalent resistance by saying, taking the product of the two resistors, dividing by the sum. So in the previous example, if you remember, so let me just show you that again. Here. Previous examples over here. Okay, so I'm not writing here. So remember the previous examples we had, and this only applies to two resistors, right? So just be careful. For some reason I can't actually. Oh, there we go. So remember we had a six and a 4 in parallel. Just ignore all three for now. So if I use the product sum rule, so 4 and 6 is in parallel. Like I said, we take the product, so it's 6 times 4 over 6 plus 4, and our equivalent resistance was 2.4. Remember, can you just quickly do that just to confirm? And you should get 2.4 ohms. So now I learned another small technique. Is when you have two resistors in parallel, you can quickly use product sum rule. So you times the two resistance divided by the sum of the two resistors. Is that clear to everyone? So I'm just showing you new techniques to analyze circuits. For the next 2 weeks, you'll be looking at circuit analysis. Thank you very much. Okay, let's just go back. Question? The question? What is that? Where to? Hello? You know, wait to raise a hand or something, or was it? Oh, I'm not sure. Okay. Anyway, let's proceed. Now, just like the voltage division rule, we have something called the current divider rule, right? Current division. So how this works is now, if we have the total current coming in, we can find the individual currents of the resistance. Similar to the VDR, where we're able to find the voltage in a series. This is only applicable to parallel. So how it works is we must have a current source coming into a parallel arrangement, and if you want to find the current in one resistor, you take the source times the one you don't want, divided by the sum of the two resistors. So I hope that is clear to everyone. So remember, in the series with the voltage divider rule, take the voltage source times with the one you want. And in this case, you have a current source coming in, and time with the resistor to find the resistor in this case, let's say it's I1 and I2, right? So if you want to find I2, you're going to take the current source times by R1, the one you don't want, divided by the two resistors, sum of them. I hope it's clear to everyone. And of course, you can do the same thing for three resistors in parallel. So what you do, you need to first find so if you're looking for I3, for instance, right? So you want I3, the current's coming in there, you got to sum up, find the equivalent resistance of R1 and R2. That will form one resistor. So basically making into a two-branch circuit, and then you have to say times by the equivalent, and then divided by the addition of the two. So I hope that everyone understands that. So let's say this actually reads a branch current is a product of the supply current and the equivalent resistance of the rest of the circuit divided by the sum of the equivalent resistance of the rest of the circuit plus the branch resistance. So the key here to understand is series voltage division you can use there, but use the one you want. For current division, the current source, parallel circuit, and one you don't want. So what I'm going to do now is illustrate this new technique. And like I said, this is new techniques. If you're familiar with your old school long way, feel free to do that. So what I'd like us to do, get your books ready, and we're going to try to solve this example. And of course, the idea here is to use your current division rule. So what did I want first? And also our product sum rule. They want us to find the supply current and the current flowing through each resistor and the potential difference across. Let's see. Okay, let me just escape, copy this. Back to my board again. So the question will probably state use voltage division or and current division. So I'm just making you aware of that. I didn't show the marks of the previous one, but okay, that was good enough. So let me just quickly share my board again. Oh, what am I sharing? Right, here we go. So what is the first step here? What will be your first approach? Michaela, what will be your first approach here? So this question is coming from John Birds. I did mention to you, I'm using two textbooks. So yeah, the main one and this one. Anyone? First point? Jason. Mr. Neto, you have something to say? Oh, can't see the values, okay.
Yeah, so I think we have to find the equivalent resistance first.
Exactly, thank you very much, Chief. This man has a distinction already. Can you see the values now? That is a bit blurry. Okay, so we're going to use a product sum rule now. So that's going to be now for R2 and R3. I'm using the resistor label here. So it's 6 times 2, 2 plus 6 product sum, right? So I hope it looks like a 6 here. 1.5 ohms, right? So now what we have now again is a simple CD circuit. So I'll just re-sketch that again. Guys, this is still child's play. This it's gonna get real soon. I don't need to write that. I'm just gonna write my voltage source here. Put it in the battery is fine. Okay, so on supply current, that's gonna be easy. Series circuit now. Should we do it over here? So I total, if you want, or I, word I, doesn't really matter. It's going to be 200 volts. Then of course it's going to be 2.5 plus 4 plus 1.5. That should be fairly easy. Our total current is 25 amps. It's a good amount of amps there. Okay. That looks good. And then there's a total supply current, and then of course the current flowing through each resistor. So we know through our I1, which is through this resistor, the current is going to be 25 amps. Also through R4, that's going to be, or I1, I4, they're all equal to each other. Do you guys agree with me? Fantastic, right? So now we're going to use our new tricks. So now we know this 1.5, that is actually a 6 and a 2, and that's going to be, and that's in parallel, right? So now we can use current division. So I'll just do it over here. So that's going to be, what's it, 25 coming in, splits up, whoop, like this, goes back. So this is I2, I3. I3, it's supposed to be I2. Okay. So what do we use now? We can use good old current division. Of course, we could have done the alternative as well, but we'll get the alternative now. Guys, when you're doing engineering studies and when you're following my lectures, what you must be taking is concepts, not memory. Understand the concept. Once you understand the concept, you're always going to win. It's like 1 plus 1 equals 2. It can only be that. Look for the concepts. So, and of course, know the techniques. So we're using current division. We want to find, so for us to find I2, what did I say we must do? Take the current source and times by which one? What do we times by?
The one that we don't want.
100%, the one we don't want.
Okay.
Exactly. I've got a bunch of excellent students here. So that's times 2. And then it'll be 2 plus 6. So then we have 50 divided by, say, 8. And that's some value which I do not know. That will give you 6.25. That's correct. 25 times 2. 2 plus. Okay, that's good. There is a low resistance, so it's okay. So let's have a look at the next one. So for us to find what do over here? I3 is going to be 25 times the other one. So I3 we got to times by 6 now, and it's still 2 plus. I hope that's correct here. So I2, the one we I2 we want I2. Yeah, the one we don't want I3. Yeah, okay, that looks good. What you guys get? 18.75 amps. And of course, if you add this together, you should get 25 amps. So that's how you know you're correct. 6.25 plus 18.75 should give you 25. Yeah, and of course, the one with the higher resistance, we can get more current here. Okay, is everyone happy with this? Great. Is there any questions here? Okay, so the one, the potential difference across each resistor. That's fairly easy. What can we use now to do that? A newfound trickery. We can use voltage division. Right? So can someone find a voltage through V1? I just need to charge my laptop quickly. That looks possible. Let's see if it's true. So V1 will be 200 volts times 2.5, and we can sum up that resistance as 2.5 plus 1.5 plus 4. Then we should get 62.5 volts. Fantastic. V2, we can do something similar. 200 times 1.5 divided by 2.5 plus, oh, let me just get the total resistance instead of writing it out the whole time. That's 8, the bottom. So what's my next voltage? 8 times 1.5, sorry. 37.5. And of course, we can find V3 easily. I'm not going to do that. That is basically 200 minus 62.5 plus 37.5, or minus 37.5. And V3 should be 100. I don't know if you guys agree with me. You can check. I'm deliberately starting off like this, showing you all the potential ways you can solve it. It's not a one way to solve this stuff. So you guys agree with me? And I just want to quickly re-show you back to this point that again, if I have the voltage across this portion, the R2 and R3, if you remember, just reconfirming and showing you that your voltage across this was what? The voltage here is, what is it? That's 37. So I'm just going to say V23. is 37.5. And if you want to find the individual currents, I just have to divide by the resistance. So the current going through I2 is going to be 37.5 divided by R2. This is usually the way that you're kind of familiar with. So divided by 6 is 6.25. It's a match, it's a match. And you're having I3, it's 37.5 divided by 2. And if you of course do that, you should get 18.75. Match. You can see exactly the same answer. Two different ways. Is everyone happy with that? Can I move on? Okay. Great stuff. So this will be our last question. There's another question for current division, but I think we're gonna just do one more, and then we're done. Then we can move on. I want to just talk about some circuit elements, basically. So I'm going to reopen my Blackboard now and treat this as a tutorial. So I will help you with this. Oh, I want you guys to give me answers while I help you. So I don't want to solve this by myself. So now we've got 1, 2, 3, 4 branches here, right? Okay, so everyone can see this. Just go back, make sure everyone. Okay, so what do they want here? They want the current Ix. Yeah, right. So you can call it whatever you want. Essentially, I'm not too worried. So on you, I want you to use voltage division and current division to find current going through here. Again, this problem is in John Bird. Electrical circuit theory and technology. So let's see you find that current. Who is competent? So I'll give you guys 5 minutes to try, and then I will come in after 5 minutes. Has anyone solved it? You guys are awfully quiet. You guys get it? Can I try to solve it? Mr. Neto, we're still there. Okay, I'll start at quarter past. See if you guys have managed to figure it out. All right, okay, so we're back and you start to solve IX. So the first approach, which I recommend, is we have to find the anyone there? Oh, fantastic. Um, we have to make sure that we get the 2 and 8 in parallel, right? So, oh, hang on here. My pin not active now. Okay, right. So we have to first get the 8 and the 2 in parallel, right? So that's our first job. So we can use a product sum rule over here. We can say 8 times 2, 2 plus 8. And if you get that, we should get 1.6 ohms. So I hope everyone agrees with me so far. Then I should actually do this here. Let me just ignore all of this quickly. Let me write it over here. Oh, so I'm going to sketch my circuit now. So we've got the 2, got the 9, and you've got 1.4, and this now you're putting in parallel. So that's my new circuit. Okay, just give me a 17 volts. So our new circuit, like I said, it's R2, equivalent with 8, so it's product sum. So I hope you guys got this. Okay, that's great. Next step, that's 1.6 ohms, right? What do we have to do? We can add up this two, 1.6 and 1.4 is in series. Do you guys agree with me? Are you guys still there? That's 3 ohms. And then 3 and then a 9 will be in parallel. You guys agree with me there? So 3 and 9 is in parallel, right? So we add those, that becomes 3. Okay, great. Thank you guys. Okay, so then I'm going to just do the calculation here. So that's 3 and 9. That's 9 times 3, 9 plus 3. That gives you 2.25 ohms. And of course, we have a simple series circuit once again, if that's correct. I hope you got this for at least 2.25 ohms. Right. Back this way, 17 volts. So what would be the next step? What did you guys advise? What would be your next step? What did you do? Anyone? We can go the current division road, multi-division road. Anyone? Mr. Neto, what did you do? You guys still here, bro? Okay. So the next step what we can do, oh, there we go. So response, find total current. Yes, we can do that. That's correct. This is one way, of course, doing this. This would be 17 divided by 2.25 plus 2. Of course, there's a simple series circuit, and our current should be 4 amps. I think you guys should agree with me. Now, what we can do now is that we have a total current of 4 amps going through the 2.25 resistor, right? So if I'm going to start to resketch this, I'm going to resketch it over here. So this goes like this. It's that's 4 amps, sorry, coming in. I'm expanding my, I'm basically going backwards now to re-expand my circuit. So we're reverting back to this, and we are looking for, remember this current over here. This current here, that's the IX current, right? So what we're going to do now, we have to find the current going through 3 ohm, and of course this 3 ohm can be rebroken up again further into 1.4 and 1.6, but because in series, it will be the same current going through the 1.6 ohm, if that makes sense. So I'm just going to quickly re-expand this. So like this. Just so that you get an idea. So you can just quickly see it, me breaking it down for you. Okay, so it's the same current. So what I do now, I can use my current division. So it's the same resistor, guys. It's just 3. I'm just showing you it's the same current. And the reason why we're going through this, so because remember we want the current going through the 1.6, the 1.6 resistor, so we can use current division again. So then what we do now, we say I'm going to call it I3 now, is 4 amps times the one we don't want, if you remember, which is 9. And then we say 9 plus 3. You guys agree with me there? And that's 36 divided by 12, which will give you 3 amps. So now we have the current flowing through here. We know this. We know what's this through here. We have 3 amps, and of course, going through here is 1 amp. That's in case you need to know that. Right? Now, at the 1.6, I'm basically reopening. I'm zooming in further. That's also in what do you call this? That's also in parallel, but it was the 2 and the 8. And then we do exactly the same thing. We can say I current 8 equals 2, the one we don't want, of course. The one IX, 2 times 3 over 8 plus 2, which is 6 over 10. So it's 3 times the 3 times 2, 6 over 10, yeah. And this will give us 0.6 amps. Is everyone comfortable with this? That is one way of doing it. And of course, then we can do voltage division, find the voltage across there, and then carry on. Is everyone happy with this? Jason, did you find Mr. Neto, Olwetu? You guys get it? It's going to get involved now. Okay, great. So now let's take a 5-minute break quickly, and then we're going to start on the next chapter, chapter 2, where we do DC network theorem. So it's also circuits, so and we'll be doing Kirchhoff law, so you guys are aware of it to a degree. So let's take a 5-minute break, and then we'll start on chapter 2. Thank you. See you now. And we will, of course, end at 12 o'clock. See you now.